sorry, I don't manage to go to the next page. Okay. Now I can state the main theorem. So the first point is that we can prove that for any n greater than or equal to 2, we can construct a countable family xi of nice, say, smooth geometrically integral k-varieties over k that satisfies the required properties. So for any field extension L over k, of course, as usual, we have to assume that the field L is infinite. Then the cohomology class vanishes in Hn of L if and only if one of the xi's has a rational point over L. So this is what I called the splitting family before. And in addition, we can choose the family to be an invariety, which is it is indexed. So yeah, this is countable. So we can choose I to be the set of positive integers, and the xi's are given with closed immersion xi into xi plus 1. And so this is what I call an invariety. And the second point of the theorem is that if n equals 2, then the variety xi can be replaced by a single smooth geometrically integral variety, so which is just what I called a nice splitting variety. So for H2, everything works well, but for higher n's, we only manage to get something a bit more general than a single variety. So this is the theorem I want to explain. And I want to mention that the n equals 2 case recovers a result by Krashen in 2016. And I have to say that the proofs are really different. Okay. So let me now explain the strategy of proof and how do we construct the varieties. So there are essentially 3 steps in the proof. So the first one is to, so you start with A, this finite Galois module. So it could be mu p or mu p to the tensor n, or any Galois module that you can imagine, finite Galois module, sorry. You take an integer d such that d times a equals 0, so the exponent of a, for instance. And we can interpret a cohomology class x in Hn of A as a Yoneda extension. A Yoneda extension, n extension, so an extension with n terms, in the category of distortion finite Galois modules. So by this, I mean exactly what is written now. So you take an exact sequence starting with B. Okay, so this is an exact sequence like this with A and B on the right and on the left. So A is the A here. Sorry, the A here is the same as the A of the cohomology here. Okay, and B, it will be the trivial. It will be Z mod DZ. Okay. So, and the EIs will be just finite Galois modules killed by D. Okay, so this is a Yoneda n extension. And so the first step is to do this change of language. And then we will formulate the triviality of the cohomology class X, which is the same as the triviality of the class of the n extension mentioned before, as a lifting problem. So what I will call a lifting problem. So I will start with a morphism of group schemes and a torsor and start with a morphism from H to G, okay, and a torsor, say over some base, so it will be K, spec of K, under G. So H and G are K groups, so algebraic groups of a K, And you take a torsor under G, and you ask if P comes from a torsor under H. Okay, and so we will formulate the question of the problem of trivializing the Yoneda extension as a problem of lifting a torsor for a morphism of group schemes. Okay, I will give details later. And the third step of the proof is to construct a nice variety that decides whether a lifting problem has a solution or not. Okay, so decides exactly means the same thing as before. So I would like to have a nice variety that has a rational points if and only if the lifting problem has a solution. Okay, so lifting problem for torsors. So this is the strategy. Okay, so I will now concentrate on the first step. So I will talk a little about Yoneda extensions, and I will denote by xn. So n is the same n as so the n here is the same n as hn we started with before. K is a base field, and D is so D here is defined as the exponent of A. Okay, and K is a base field. So xn kd of AB will be the group of equivalence classes of n extensions of A by B, in the category of distortion Galois modules. Okay, so K means we take Galois modules for the absolute Galois group of K, and D means we consider only the only groups appearing. The groups appearing are only distortion finite groups. Okay, so this is the group I want to consider. And so I recall here that an n extension is just an exact sequence like this. So it's of Galois modules if we are in the category of Galois modules. And I won't give the details, but there is a natural notion of first morphisms of such extensions. So I will ask a morphism just to be a morphism of complexes, which is the identity on both A and B. And we will say that two so we will say that two extensions E1 and E2 are equivalent. Well, the equivalence relation is generated by the following one. So if there is, well, you take, in fact, it can be defined by this formula. So if there is another extension E and morphisms like this, and you can also put the arrows in the other directions on both sides. So you take the equivalence relation given by these morphisms, and you get a nice relations, and so you get now the group of equivalence classes. So there is also a group structure as usual on the set of n extension, and you get the group xn that I mentioned before. Okay, this is kind of classical. And what is interesting for our main problem is that there is a natural isomorphism between the X group and the Galois cohomology group. Okay, so if you choose one of the, so there was A and B. If you choose the first coefficient to be Z mod dz, then you get this isomorphism. So you could either prove it by using derived functors and the comparison between derived xn and Yoneda xn, or you can define it explicitly by an iterated co-boundary map. You start for when you have an n extension, then you can map the element 1 in Z mod dz to hn of A by iterating co-boundary maps. Okay, so you have this isomorphism of groups, and now instead of working with cohomology classes, we will work with n extensions. So we will see our initial cohomology class X as a n extension. And we'll denote it by so A on the left, Z mod dz on the right, and the groups in between will be called EIs. Okay? This will be the notation that we'll keep until the end. So this is our cohomology class. And the EIs are Galois modules, and the FIs are morphisms of Galois modules. Okay? Right? Okay. So now we just change the nature of objects. We can now follow the second step, which is about going from n extensions to lifting problems for torsors. So we forget now Galois cohomology, and we work with Yoneda extension. So it's a slightly more general setting. So you take any A and B that are finite Galois modules, and you just assume, this assumption here will be important. You just assume that A or B is free as a Z mod dz module. So just a Z over dz to the n if you forget the Galois action. Okay? So one of those is like this. So for instance, for Galois cohomology, A is Z mod dz, so it's free. Okay? So it applies in particular to Galois cohomology. And we start with the Yoneda extension E, and we would like to construct a splitting variety defined as before. And in fact, yes, our main theorem can be stating in this more general setting of Yoneda extensions without talking about Galois cohomology. So E is written as before. And we know the following useful fact, which is really a simple lemma. You can find a variant of this in the beginning of one of the Bourbaki books. So the class of the extension E is trivial. So the definition is it's not so obvious by definition, because the definition of the equivalence is not so easy in Yoneda n extension, but this fact is not very difficult to prove. So the class is trivial if and only if you can find what I will call, so from now on, when I will write diagram like this, a diagram will always mean something like this. So the first line is the extension you started with. So the first line is E. And the second line is n-1 extension. Okay? You have n extension at the top level and an n-1 extension below. And here you have the same En with the identity map. And you change, of course, the EIs to some FIs, F1 to Fn-1. And you want to have a commutative diagram like this. So the first line is exact, the second line is exact, and you have vertical morphism, which are the identity on the left and on the right. Okay? If you have such a diagram, then the class is trivial in the X group, and equivalently, if the class is trivial, then you have such a diagram. So we will use diagrams like this to construct the splitting variety. So if you have such a picture like this, so with two lines, so your diagrams with two lines like this, you can consider two finite groups, which will be very useful. So the automorphism of the first line of the extension and the automorphisms of the diagram itself. Okay? You just consider the extension and the diagram as abelian groups, as complexes and diagrams of abelian groups. So you forget the Galois action. So you define the automorphism groups, forgetting the Galois action, okay? And you get these two finite groups. Okay? They are finite because everything is finite in this diagram. Okay? And now if we forget the second row, you get a natural morphism. Forgetting about what happens on the second row, you get a natural morphism from the automorphism of the diagram to the automorphism of the n extension you started with. Okay? And as usual, the Galois action on the extension is given by a morphism from the Galois group to the automorphism of the extension. And we can now reformulate the triviality condition in a more, say, geometrical way. So it will be geometrical on the next slide, not on this one. So you have the extension E. The class is trivial if and only if you can find first a diagram D, and so a diagram D of without any Galois action, so in the category of abelian groups, and you can lift P, which gives the Galois action on E. You can lift it to D. Okay, so it just means that you can find a diagram of Galois modules, but it just in terms of embedding problems. So you have the vertical morphism from gamma to the automorphism of E, and you ask, can you lift it to the automorphism of D for one diagram D? Okay, phi is the morphism defined before. So,
pardon.
Yes.
Sorry, can you repeat, because I think there was a problem with the sound. I had a problem.
Oh, sorry. Yes, I can repeat it.
30 seconds. Yes.
Okay, I can repeat this slide, no problem. So I was saying that so you start with a class E, which is an N extension, and so what I said before proved that if the extension is the class of the extension is trivial, you can find first a diagram of abelian groups D without you forget the Galois action. So first you look for a diagram D of abelian groups, and you ask, can you lift the Galois action on E to a Galois action on the whole diagram? So it can be expressed as an embedding problem as here. So the question is, how can we so we will now make it more geometrical in order to build this splitting variety. Okay, so this is an embedding problem, and then we will move to some lifting problem for torsors. So here we had a map from a map from gamma to automorphism of E, which can be seen as a one cocycle. So, or it can be seen as a torsor. So associated to this data of P from gamma to the automorphism of E, we have a natural torsor P over the base field K, which is a torsor under the constant group automorphism of E. And the question now is, so the embedding problem can be summarized as a lifting problem as follows. So the class of the extension E is trivial if and only if you can find first a diagram D of abelian group, and in a way that the torsor P that we started with, which corresponds exactly to the extension E, can be lifted via the morphism phi to a torsor not under the automorphism of the extension, but under the automorphism of the diagram, the two rows diagram. Okay. So more precisely, so the triviality of the class is detected by the existence of D, and so D defines the group automorphism of D here, and then you would like to lift the given torsor PE to one torsor Q. Okay. So this is what I call what I will call a lifting problem. So the data is exactly P over K, a torsor under haute E, and the morphism here. This is the data. And we ask, can we lift this torsor for the morphism phi? Is there an odd D torsor that lifts PE? Okay, this is what I will call the lifting problem for torsors. right? Okay. So the third step is to construct the lifting variety. So a variety that tells you if the lifting problem has a solution or not. So we need to construct these lifting varieties, and this step is a variant of a now classical construction of versal torsors. So let me explain it. So I fix morphism phi from H to G, a morphism of linear algebraic K groups. Okay, so H and G will be the automorphisms of diagrams and extensions that I mentioned before in the applications. But here we can work with any linear groups, H and G. And you start with P over K, a G torsor under the group on the right of the morphism, the target group. Okay, so this is the setting. And I will define what the lifting variety should be. So a variety X will be called the lifting variety if there is a nice diagram like this. So it is a diagram of torsors where, so on the right, you have the torsor P extended to X. Okay, you started from a torsor P here, you extend it to the base X. And Q is a torsor under, so P is a torsor under G, and Q is a torsor under H, the other group. And you want the morphism between them to be phi equivariant. So H acts on Q and P through phi, and you want this diagram to be H equivariant. Okay, compatible with the morphism phi given at the beginning. So if you have such a diagram of torsors over X, and you ask this diagram to be versal in some sense, so by which I mean as soon as you take an extension of L of K and you take a similar diagram over L, so this is a lifting diagram over L. So if you can lift P over L, then this lift comes from a specialization of the big diagram above. Okay, so it's really a variant of the construction of a versal torsor which is classical in this setting. I want more than just the second diagram is a specialization of the first one, but it is a specialization for a lot of L points in X. So the set of points in XL for which the second diagram is a specialization of the first one should be Zariski dense. Okay. So I want this. I take this as a definition of a lifting variety. And so in particular, it solves our problem of detecting whether the torsor under G comes from a torsor under H or not. Okay. But we know more. We know that the set of such points is Zariski dense. Okay. So theorem, lifting varieties exist. So this is what I will explain now. So how do we construct them? Well, we copy the construction of versal torsors, and then we adapt it a little by twisting it. So you start as usual by considering a finite dimensional vector space V with a nice generically free linear action of H. Okay. And then, I'm sorry, you choose a dense open subset of the affine space corresponding to your vector space, which is stable by H, and for which you have a nice quotient, which is a torsor. So this is exactly the construction here. This is the construction of the versal torsor for H, right? So this is completely classical. And then you have to do the same for G, and you have to put the given torsor P into the picture. So you construct X to be the diagonal quotient of P. So P is the torsor. So recall that the setting, we fixed some torsor P under G, over spec K, and a morphism phi from H to G. So this is the setting. And we want to lift G to H. So we construct X as the quotient of P times Q prime. So the G torsor that is fixed times the versal torsor for H, and we quotient it by H. That acts on both sides using the morphism phi. And of course, this quotient can be, we can quotient more and then send X to the quotient of the initial, the base of the versal torsors, right? So we have an orthogonal morphism from X to Y, and then, so equivalently, if we speak about twisting torsors, this X is just a twist of the initial torsor P by the versal torsor Q prime. So it's a twist of a G torsor by a H torsor using the compatibility given by phi. Okay. And then you put Q prime and this twist together in the following diagram. So I define this as versal. This is a versal torsor for H, one versal torsor for H, sorry. And this is a twist. It's written here. Sorry. This is a twist of a G torsor by the versal torsor Q prime. Both of them are torsors are defined over Y, and you take the Cartesian product here. So you define something that you call Q. Of course, Q over X will be a H torsor because it comes from the H torsor Q prime by base change. So it's a base change of the versal torsor. Okay. And this Q over X will be the one part of the big triangle we were looking for. Okay. So let us now check that this construction gives what we want. So by construction of this Q, and in fact using the fact that essentially the definition of the twist of the torsor, you have the following property. So if you want to describe S points of X, so recall that X is this twist here on the bottom. So it will be the base of our lifting. It will be our lifting variety, so the base of our lifting triangle that I mentioned before. So S point in X is exactly a morphism from Q prime to P, equivariant under H. So this is a classical, this is a general identification, a natural property of twists. Sorry. So in particular, if you take if you take S to be X, and if you take the identity of X, you get this natural diagram of torsors. So you have Q to X to Q to H that was defined on the previous slides, and here you have the torsor you started with over K. You extend it to K to X, sorry, and you have a natural map between those coming from the universal property of, in some sense, of the twist. Okay, so you have such a triangle, which looks very much like the one we are looking for. So we managed to lift the torsor P over the base X to some torsor under the group H. And now we need to prove that it satisfies the required property, which means that this is versal for the lifting property. So any lift of P over any field extension of, say, K So any lift of G is a specialization of this universal lift, of this versal lift. And this is done exactly as in the setting of the versal torsors, using as a key property, of course, the Hilbert-90 theorem. Okay, so we managed to produce these varieties that detects whether a torsor lifts to a bigger group or not. Okay, and we also want to have nice geometric properties for the variety X. So we can prove easily that if X is X will be smooth and geometrically unirational as soon as the morphism phi is surjective, or if the group G is smooth and connected. So for our application, of course, this surjectivity assumption will be the one we will use, because our groups, I recall that our groups will be finite in the end, because they will be the automorphism groups of our n extension capital E. Okay, so in the end, our varieties will have these nice geometric properties because of the by construction. Okay, because of the surjectivity property that we will have to check the geometry, the surjective property. Sorry. So how do we conclude the proof now that we had our 3 steps? So we managed to construct. So I will recall here what we constructed in the case n equals 2. So this is a simple case where everything works well, and we can construct a single splitting variety for any cohomology class. So start with your cohomology class X. It corresponds to a 2 extension of d-torsion finite Galois modules, as before. Okay. Of course, here B is Z mod dZ, but we don't care. We only need to use that B is free. I will explain why. Up to placing E by an equivalent extension, the equivalent relation that I mentioned before, we can also make E2, so E2 here, so B is free, and E2, we can make it free. Just to take some free abelian group with a Galois module structure that subject to E2, to the initial E2, and you just pull back the extension and it works. So B and E2 are free. And then using the lemma I mentioned at the beginning, we know that X, the cohomology class, is trivial if and only if you can find a diagram like this. The same diagram as before, except that we have only n equals 2 here. Okay. And what is very simple in this case is that since, okay, here E2 and B are free, so F1 has to be free, and phi1, of course, it's easy to see that phi1 has to be injective here. Okay. Using these very simple properties, you can check that the following lemma holds. So up to isomorphism, there is a unique such diagram in the category of abelian groups. So if you forget about the Galois action, there is only one way to construct such a diagram up to isomorphism of diagrams, to equivalence of diagrams. So it is very easy to prove, and this unicity will explains why we get a single variety and not a family of varieties in the end. Okay, this is why n equals 2 is much simpler than n greater than or equal to 2, and greater than or equal to 3. Sorry. So I don't explain this lemma; it's easy to prove. And so now we can put everything together. So the Galois action on the 2 extension correspond to a torsor under the automorphism group. And one can construct the lifting varieties that I mentioned before associated to this torsor and to the morphism, starting from the automorphism of the given, the unique diagram that I mentioned before, to the extension we started with. So you have this morphism and you have a torsor under the automorphism of E. So you can construct the lifting varieties that detects if the torsor lifts or not. And this variety X satisfies exactly what we want. The variety has an L point if and only if the class is trivial. And in addition, since F1 that I mentioned before is free as a Z mod DZ module, we get that the morphism between the automorphism groups here, this morphism is surjective. And I mentioned before that it implies that the variety X has to be very nice, so in particular smooth and geometrically unirational. So it's a quite nice splitting variety. And as a remark, I can say that in the special case that when A is mu D, so X is just a class of a central simple algebra of index D, then our splitting variety is stably birational to the Savry-Brewer variety of R, which is quite natural, but not so easy to check maybe. Okay, so but it can be applied to more general coefficients, right? So, and if I want to summarize, in fact we prove a slightly more general result than the splitting result I mentioned at the beginning, because we can state the result for more general extensions. So A is not necessarily Z mod DZ. It could be any finite Galois module, provided that A or B is free. Okay, the Galois action on it can be arbitrary. Then there is always, for such an extension, there is always a nice splitting variety. This is what we prove for n equals 2. And the statement is symmetric in A and B because of the Pontryagin duality. So you can exchange the role of A and B in the extension setting, right? This is how we get some symmetry in the statement. What happens now in the general case when you have n greater than or equal to 3? We did not manage to get a single splitting variety by our methods here. So we only get a countable family, a nice countable family of splitting varieties. So nice splitting family. The construction is more technical, but I will just explain the main steps. So we start now with not just a 2 extension, but an n extension. Okay, and we can always assume that B is free because if it comes from Galois cohomology, it's Z mod DZ. So we can assume that B is free. We can easily assume that En is also free. So B and En are free. This is easy, same method as in the n equals 2 case. And the more technical point is now, so we can restrict to diagrams. So I recall that a diagram is in my talk, a diagram has 2 rows. Okay, the first one is E, the exact sequence I mentioned here. The second one is an n-1 extension. So we can restrict to diagrams that are both injective and free. So by injective, I mean that the vertical maps in the diagram, so from E to the row that trivialize the extension, the vertical maps has to be injective. And we say that the diagram is free when the second row is made of free Z mod DZ modules. Okay, so but this second step means that the variety, if the extension is trivial, then it can always be trivialized by such an injective free diagram. Okay, we don't have to take into account all kinds of diagrams, only this specific kind of diagrams. And among this small family of diagrams, we can restrict to an explicit family, a countable explicit family of injective diagrams, which look like this. So I will only write the second row of the diagram because the first one is the exact sequence E that is here. Okay. So the second row of the diagrams we only need to deal with is as follows. So it's really made of 3 Z mod DZ modules, because I recall that both EN and B are free also. And the maps are explicit. I didn't write the details, but they're given by projections to 1/2 of the coordinates. So I don't want to explain the details, but everything is explicit in this family of diagrams. And what is nice is that these diagrams are compatible with one another. So it's really a family. You have injective morphism from the diagram dm to the diagram dm+1, which will make the ind structure in the end. Okay. And using the freeness of the groups appearing here, you can prove that the map between the automorphism groups, so from the automorphism groups of the diagrams to the automorphism group of the extension, these maps are surjective, which will be good to ensure the nice geometric properties of the varieties in the end. So this is only group theory, it's not difficult. And what is not easy to prove is that this explicit family here is cofinal in some sense, by which I mean if the extension is trivial, if and only if there is a Galois action on one of those explicit diagrams dm. Okay, so it proves that the lifting varieties that you can associate to these diagrams by the same process as before, they are a splitting family for the extension E. And in addition, of course, the inclusion of the diagrams give rise to closed immersions between the corresponding splitting varieties by some easy functoriality. And so it defines the required invariety that detects the triviality of the extension, hence of the cohomology class we started with. So to sum up, we proved a slightly more general result as before, which can be stated for any, not only for Galois cohomology classes, but for any extensions, provided that one either A or B is free. Then you can prove that in this setting, as soon as n is bigger than 2, there exists a nice invariety that detects the splitting, the triviality of the extension. So this is the general case. We do not know yet if a single variety is enough. And once again, the statement is symmetric in A and B because of this duality in the world of n extensions. And this is the end of my talk, so I want to thank you for your attention.
Okay.
Thank you.
So clap. Okay, so maybe questions, comment on the talk? So you can also use, the chat if you.
So for n equals 3, and say if you assume for n equals 3, and if you assume that your class is a symbol, can you still get an actual variety?
Well, in fact, we don't see precisely how the assumption that the class is a symbol translates in terms of n extensions and in terms of our constructions. So we cannot really deduce from our constructions more precise results for symbols. We didn't manage to do this. Maybe it's possible, but some extra work has to be done.
Other questions?
You mentioned at the beginning that X is projective, or the Xi's are projective, but your construction doesn't seem to do that.
You're right.
And for n equals 2, you said that it's stably isomorphic to something that's Brauer-Severi variety and therefore projective. Can you see that in general, that it can be replaced by something that is projective?
Good question. Yes, you're right. In the construction by Rost, the variety is projective. So it's important in the proof that the variety is projective. So in our construction, of course, the variety is not projective. And so we only have some, so the birationality, so the stable birationality, well, to prove that our varieties are stably birational to some well-known projective varieties, we only check it for Sevry-Brouwer varieties, so for n equals 2. We didn't manage to prove similar comparison for higher hands. So I cannot really answer to your question. But there is one of the main difference between the construction by Rost and our construction is this lack of projectivity in our work. You're right.
Okay, who is next?
I have a question. Hello. So at the beginning, you started with rational points versus 0 cycles of degree 1. Now, on the cohomology side, it's obvious that if your class is killed by an extension of coprime degree, then you have a rational point. So your varieties have the property that if they have a 0 cycle of degree 1, then they have a rational point over any field.
I see. Yeah.
Well, that's a fact. That's all.
Yeah, that's a fact. That's a fact. I was just wondering if there was some. No. You're right. Yeah, you're right. It's a fact. We decided to work with rational point because it was easier to handle. But you're right. Yeah. Our family of varieties is a family of nice variety for which the existence of 0 cycles of, say, degree
1 over a given field extension.
Yeah, this is true of any field extension. Okay. Yeah, this is nice. You're right. Thank you.
Okay, so there is a remark by Mathieu saying that only the n variety has this property. It's not clear about the individual varieties.
Oh yeah, he's right. Yeah. Of course. Thank you, Mathieu. Yeah. It's only the family as a whole that has a variety mentioned by Cohomology. Thank you.
Okay, so maybe last question. I don't know. Okay. So there is a talk next week, same time by Cameron Reuser, and so we can thank the speaker again. Okay. Bye.
Bye. Thank you.
See you next week.